Hey guys, hello and welcome or welcome back to my channel. This is Kshitij, and on this channel we talk about robotics, research and academia. This is the sixth lecture of the TT101 lecture series on basics of mobile robotics. Today we are looking at state estimation, so going a step beyond perception. This is a brief overview of the lecture for the day, and it will build on the discussion where we ended the previous lecture. So in case if you have missed the previous lecture or any of the ones that we have done in the past, you can find the link to the playlist in the I button above and also in the description box below. So we will do a quick recap of what we've been discussing so far, and then we'll build on the discussion with some state estimation, mapping, localization, uncertainty, and filters. So previously we discussed perception and perceptual pipelines for some of the most prominent sensing modalities such as audio and vision. And then we looked into illusions, aliasing, and synesthesia, which might interfere with how you perceive the environment. And some of them also apply to how a robot perceives the environment. In today's lecture, we are going beyond perception and we are looking into state estimation because, we are trying to answer the question, so the robot is able to perceive the environment. So what? What can it do with that? So we saw that sensing is a bottom-up process of relaying the external stimuli as is, and you just receive the raw information and you just pass it along. Whereas perception is the top-down process where you add context to the stimuli, you organize and interpret the information and try to make some sense out of it. So once you're able to perceive the environment, or by you I mean the robot, so once the robot is able to perceive the environment, it needs to be able to interpret what is its state at the time instance t. Now, the state of a robot at any time instant t is dependent on the context and the scenario in which the robot is deployed. But for an example, to give you an intuitive understanding of what a state would look like, typically it would consider things like position, orientation, velocity, partial map of the environment until that time instant t, whatever the robot has explored around in its space, couple of other things depending on context, and so on. So state could have a lot of different parameters involved inside. And we will define a few terms here in terms of the state. So first of all, there is this thing called complete state. Now, a state of a robot can comprise of a lot of parameters, as I just explained. Depending on context, the definition of what exactly is inside a state is changing. So a state is considered to be as complete if the future state at a time instant t+1, where t is the current instant, is independent of the history of all the states starting from x0, where x is the state and 0 is at t equals to 0, so the start of the mission, and t-1 is the previous instance. So if you are able to get rid of the entire history and you're still able to understand what the next state is going to be based on the current state, then you are able to have a complete state. And this is known as a Markovian property, where the future is independent of the past. Then there is this state called the world state, which is the actual ground truth state of the real world, often not fully and accurately observable by the robot, because there are a lot of limitations, such as what the sensor can and cannot measure. Then there is a lot of noise involved. So the robot doesn't really know the exact ground truth, but if there is an external observer, somewhat like a God's eye, you're able to understand what the ground truth is, then that would be the world state. What the robot is able to understand in terms of the state is what is called as the belief state, which is what the robot believes the world to look like. So the idea would be to have the belief state be as close to the world state as possible. Now, why are we talking about state estimation? So remember this slide from our previous lecture where we said there is this real world. We considered an indoor office environment and we were talking about various kinds of maps. So let's say here you're doing some sort of edge detection and your perceived world would look somewhat like this. And then you would try to figure out what the robot state is, which means the robot is trying to figure out where it is, what is the position, and then if it were to apply some velocities, then what kind of actions would it be able to take given the current state where the robot is in and how the world looks like. And then it's a closed loop cycle. So every time the robot moves, things change. The perceived environment changes. You are able to explore more parts of the environment because you've gone beyond your previous sensing radius. So you've expanded your overview of the space, and then you need to update the thing. So that's why you have to keep on estimating over and over again. But the question is, why estimation, right? So the thing is, remember what I told you about what is inside a state. So it could be position, velocity, partial map of the environment, so on and so forth. But sensors cannot directly perceive the state. What the sensors can give you, for instance, if you take an example of odometry, maybe you get some partial information about how much your wheels have spun from a certain time instant to the current time. And then because you know the wheel radius and you assume that the wheel is not slipping, you're then able to map it to some velocities, right? Same way for a car, the speedometer doesn't directly measure speed. It's basically from the amount of spins that the wheel has taken, you then map it to velocity, right? So the sensors don't directly perceive the state. And that's why based on whatever raw information your sensor is able to give you, you're trying to estimate what the state is at a particular time instance. And then whether or not the state from current time to the next time is Markovian or not, that's another aspect to consider. And then because the robot is moving, or in fact, either the robot could move or things might change in the environment, maybe like in the office environment, somebody just stood up and walked away after the meeting finished, or something else changed in the environment. So these updates of the estimate of the state of a robot needs to be updated recursively. Interesting fact to note here is that in this example that I've shown you, so the robot is moving and we've considered two cases independently. So in one case, it is just translating in a straight line. And after every certain amount of time elapsed, you're trying to estimate what the robot, what's the current pose of the robot. Let's say that's the state for this scenario. And the ellipse that I've drawn around this is the sort of location uncertainty that you have at that position, because you're moving forward and you are not 100% sure, but you're kind of sure that somewhere within this region is where you should be. Things get really interesting when there is rotation involved, right? So there is the robot is moving forward, but once it starts turning, the amount of uncertainty that you have grows quite fast. And the more number of turns there are, the faster you end up getting lost. Okay. So recursive estimation, as I said, the robot or something in the environment changes over time. That's why you need to update your state periodically, which means if you're making a map of the environment and something in the environment, like an obstacle or an object, moved between t-1 and t, that needs to be reflected as such as well on the map as well, because the map at t-1 had that object at a different location. At t, it should have it at a different location, and the same thing applies to your robot. That's why we need to recursively update your estimate, and it normally happens in two steps. So first thing is you predict. So you remember we talked about proprioceptive or interoceptive and exteroceptive sensors. So you use the interoceptive sensors such as wheel odometry, etc., to kind of predict the next state based on the current state estimate that you have. Okay, and then you use the exteroceptive sensors to get some likelihood from information from the environment as to what your state estimate should be based on the measurements that you're getting now. And then you try to make corrections if there is some sort of offset in what you predict versus what it actually needs to be. So let's look at an example of what a recursive state estimation does. So let's say at t equals to 0, your robot is at this position, and then you give some commands for the wheels to do like one complete rotation, and the robot would then land up in a new position like this at t equals to 1. In reality, however, there is no guarantee that the wheels actually spin one full rotation, because as I said, let's say you're using a wheel encoder and it reports that it's spun by one full rotation, but maybe there was some noise and they only spun like 80% of the full rotation, or maybe they overshot and they went like 120% of the full rotation, or maybe there is some sort of slippage on the ground so that the wheels are slipping slightly. So you basically are slightly offset from where you need to be. But the robot doesn't know this, because as far as it is concerned, you give it one full rotation, the robot thinks it does one full rotation because that's what the sensors report. And then, there is some ambiguity in where it is. But if you have this landmark, for instance, like a star, you, based on, how the environment is perceived. So given the action, the environment would have looked slightly different, but now it looks slightly different because of this offset in where you should be and where you are. You could use this landmark to correct for these errors. So essentially it would look something like this, where let's say the dark images are the actual ground truth versus the lighter images are what your path you took, and you need to do recursive estimation. Now, the interesting fact here is that what happens if the robot just keeps on predicting its state for the next step without actually correcting for anything? This could happen if there are no landmarks whatsoever. But then the question for you is, what happens in that case? What is the worst case scenario look like? Okay, so we talked about various, let's say, parameters that are inside the state of a robot, right? One of them was the map of an environment. So we briefly touched upon this in the previous lectures as well, as to when we were discussing perception, right? So what does a map of an environment look like? And we talked about a few different kinds of maps as well. So here we are trying to define it more formally and revisit the concept and look into it a bit more deeper. So a map is essentially a spatial representation of the robot's environment, right? So as I said, this treasure map is a perfect example, right? So you start from somewhere, you have some landmarks, maybe a bridge, then you meet a farmer, and there would be a mountain, etc. And the cross marks the goal position, and the dashed line represents the trail that you need to take to get to the goal. So this is essentially a map. That's why it's called a treasure map, right? It's how your environment looks like, assuming it's a static environment, so nothing changes. And it shows the relationship between the various features from the perceived sensor data, okay? Where representations could be geometric, semantic, landmarks, raw measurements, could be like Wi-Fi signals, etc. So we looked at some of these in the previous examples. Now the challenge is, the sensors are noisy. They give you noisy local measurements. The map needs to be updated as the robot moves. And if you're storing way too much information, then these updates start to become a bottleneck as the robot explores more and more. This is especially challenging if you're building a map and you're not already given a map. And also if you're doing map updates. So let's say you're given a treasure map, and sometimes the path breaks and a new road is built, or there are diversions or something. So in a static map like this, those things would not be shown. But as you are venturing out, you would realize that something changed, and you need to record that information. And depending on how much information that incorporates, this thing is soon gonna get real messy. Now imagine like you're drawing very fine updates to what changed. There are a lot of paths and trails, and you're trying to map everything. Soon this map is going to have so much information, so many different trails, that you practically cannot read it anymore. It would just be like a whole mess of lines all over the place, right? Which also means there are a lot of different possible maps at that time, and the other person would just have a computational bottleneck if they're trying to interpret how to make any sense of that map. So typically, there is this nomenclature that we use for discussing maps, and especially in probabilistic terms. So the M represents the map of the environment, and X of T, where X is the state of the robot and T is the time instance. Z is typically used for instantaneous measurements. Then there's also this variable U, which are the control commands, but they are not relevant at this time. Later, when in the next few lectures, we start discussing SLAM, where the robot is actually moving, control commands will come in handy. But for the moment, we're just going to talk about the state and the measurements. And so the problem of mapping, assuming that you know where your robot is, which is why we say known robot poses, is the probability that the map is M given the history of measurements and the history of states. Now, the Markovan property we discussed is not yet incorporated into this probability function. So when you start expanding on this, at some point, if you figure out that the Markovan property exists, then this drops down to just X of t and z of t because the entire history no longer matters to us. Okay. The question for you here is that here we are talking about known robot poses. In case of unknown robot poses and you're building a map in that scenario, basically that counts for an unknown environment, right? So let's say your robot is visiting a disaster site where you had an idea of what the floor plan looked like when the building was standing, but now the building has collapsed. And the robot doesn't know where it is with respect to that map. So what would this problem look like for mapping with unknown robot poses? So just think about this in terms of a similar representation like this, but what changes if the robot poses are unknown. Okay, now various kinds of maps, right? So we talked about a few different types of maps last time, and a map essentially gives you a precise location of the features, if you're talking about a metric map, right? So we're going to classify them into broader categories. So first category is a metric map, and the example is something like this. So when you're doing like a road trip planning between two waypoints, let's say A and B, you're interested in the exact distance, right? So you get precise locations of A, precise location of B, even if there are some pit stops in the middle. You need everything to give you distance in the metric system. And that's why it's called a metric map, and it can be two-dimensional or three-dimensional. Oftentimes two-dimensional is enough, but robots operate in a 3D world. The world around us is three-dimensional, so there might be scenarios where you would need 3D. Now, typical examples of metric maps include occupancy grid maps, landmark maps, feature maps, semantic maps. So some of them we looked at some examples in the last time, but occupancy grid maps was something that we did not cover. So we're going to look at them in this lecture. One thing to understand is that we did give an example of landmark maps last time, but there is also this feature maps, right? So we talked about in the perception pipeline, we talked about features. So if you're mapping out features in an environment, oftentimes the people tend to get confused between what's the difference. So there is a very subtle difference between the two. So landmarks are essentially objects with fixed locations, and they could be natural or man-made. Like think about Eiffel Tower, which is a man-made landmark, versus a tree somewhere, let's say an ancient tree that has existed for 100 something years and it's known to be there, it's standing, it has passed the test of time, etc. That becomes a natural landmark. So there could be, those are landmarks, okay? And features are, on the other hand, very artificial and abstract data structures. So things like image gradients, intensity, corners, edges, or depending on some other perception pipeline, there could be different features, but those are artificial. And landmarks could be natural and man-made. So there's this subtle difference of what information you put on the map, and accordingly, you call it either landmark map or feature map. Now let's talk about occupancy grid map, which is the type of metric map that we have skipped so far. So this cute dog is trying to ask you, hello, anybody home? And I'll quickly explain what that means. So occupancy grid map is very popular for indoor navigation, and especially for structured and static environments, okay? And we break down the word occupancy and grid map such that the environment is discretized into grids, and then the occupancy of grid is being estimated. That's why this dog is trying to ask you, anybody home? And you do that question for every single grid once you've discretized the map into grids, okay? And if you're asking yourself, how does one discretize the environment into grid cells? Follow along. So think of this as a simple dummy environment of a typical metric map, and these polygons are your obstacles, and this is like a closed environment, so the robot doesn't go out to eternity. And we want to perform what is called a cell decomposition to get grids on this and off this environment, okay? So the first way is called exact cell decomposition, which is, you pick a feature of the object. So in this case, I'm picking corners, and you decompose the cells, the environment, to get cells such that, features of the object such as corners are like the boundary of the cell. So in this case, you will end up with getting something like 10 cells, and this is an exact cell decomposition. Another way of decomposing it is a fixed cell decomposition, which does not take into account any features of the environment, but it's like, imagine like you have a graph paper and you impose it on the top of your environment, where the grid resolution, which is the size of each of these squares in the grid cell, So each grid dimension is preset. So you don't care about what your environment looks like, and then you just simply superimpose the two things, which then gives you something very nasty sometimes. So we'll take a look at this example. So imagine there are these two obstacles and there is a very narrow space between them. So these red blocks represent free cells, right? So this cell is free here, this cell is free here. But if a robot were to figure out, to go from point A to point B using a path that does not collide with any obstacles, the obvious way to use this is to check for cells that are not occupied and then connect them with a path, and then you get to the goal. The problem here in this case is that these two cells are free. Technically, the robot would want to connect them because it doesn't see a problem why it can't, but it won't fit through the narrow space between the two obstacles. So the traversable free space disappears sometimes in narrow spaces. So cell decomposition, you have to be careful with the way you do it. And I've only covered very, very basic cell decomposition methods, so exact and fixed cell decomposition, but there is also extensions like adaptive decomposition, which means when something like this happens or around the obstacle boundary, you use a much finer resolution grid, but other times you use a much coarse resolution grid. So it's like a multi-resolution grid, and that takes care of not having these kind of problems, etc. So what does that mean in terms of the occupancy grid that we were talking about? So as I said, occupancy grid is basically discretize the environment into grids and then check the occupancy of the grid cell. Okay, so this is your grid environment, and then the cells typically have three colors. So if this is your robot, the blue lines represent the sensing cone. Then let's say it is using a typical sensor, it could be a laser rangefinder for the sake of argument in this case. Then what would happen is that this sensing cone represents the current region that the robot can sense from its current position and orientation. And it would have black cells, which represent the cells in the environment that are occupied, which means you cannot go there. These are obstacles or blocked. And then there would be white cells, which are these kind of cells here, which are free space, which means if you want to go from one grid cell to another, you're free to choose any white cell in that area. And then there would be these grayish cells, which are kind of the uncertain zone or the gray zone, so to speak, which basically means you have no idea. It's like a 50-50 case, right? So the cell could be occupied or free. Now, there are a couple of assumptions in this kind of a setting. So one is that there could be only two states for a cell. It could be either occupied or could be free. Then the cells are independent, right? So when this cell is occupied, this does not have a bearing on the next cell or the neighborhood cells being occupied or free. Every cell is independent. Now, of course, one could argue that this is not really a practical case in the real world, then, because every an obstacle would have some thickness, some edge length, etc. So there is very little chance that the next neighborhood cell would be free as well or occupied as well. Yeah, that's completely valid, but then this is a simplification assumption to make the map updates and computation complexity more manageable. So you will see quickly in just a moment as to what that means in the mathematical terms. And then another last but not least assumption is that the environment is static, because if the obstacle moves, then this grid which was previously occupied is no longer occupied in the next cell. So then you would have a trouble trying to figure out eventually is the grid occupied or not, right? And that basically, when you combine all of this information together, would render a map somewhat like this. And then depending on the quality of the sensor and the grid resolution, etc., you start to have a few different issues to deal with, such as this boundary might be a bit grainy and coarse. Maybe this is not going to be a continuous line if you have very coarse sensor. If the grid resolution is too high, then you have too much computation to deal with. If it's too low, you're going to miss out on information, etc. So yeah, it's not that really straightforward, but as you can see, it starts to look quite a bit similar to a floor plan of an environment, and especially indoor environment. So this is a very prominent kind of map to use. So if I want to go from, let's say, this part of the environment to this part, I just look for the white spaces and try and connect the path based on whatever my criteria is, maybe shortest path or quickest time, etc. Then I could just find a path given a map, right? So the problem mathematically then is the probability that the map is M is just the product of the probabilities that small m is now each grid cell. So that x, y is the coordinate of the grid cell. And in words, you basically are reading it as the probability of a map is given by the product of probabilities of each of its grid cells, and product because we had that independence assumption of each of the grid cells. So that easily allows you to do a product, and it makes computations very simple. Okay, now, as I said, one might easily argue that navigation of a robot in a real world could easily require, 3D representation of the world. For example, a drone is flying in the air in an environment, even if it is an indoor environment, but there is some height of the obstacles, there is some walls which have a height, there is some depth. So we require some sort of 3D information, but that's not possible if you're talking about occupancy grid maps in 2D, right? So that's just like a flat floor plan. So there have been extensions of occupancy grid maps, and instead of a grid cell, now you have what is called as a voxel, which represents the volume of the cell, as opposed to just occupancy. And that's why this is color graded, where different colors means different depth and height information and so on, right? So if you're curious of how this works, you could read up this paper called Octomap. This is an open source ROS library. It has been published and has been very well adapted in the ROS community and the robotics community for quite a while. And yeah, it's a very fast computation, very computationally efficient algorithm that does the same thing, occupancy grid map, but for 3D environments. We're not going to go into too much details of the algorithmic implementations just yet, and this is just an introductory lecture series, so to get you familiar with the terms and concepts. Implementation details and finer details come at a later stage, perhaps in the next lecture series or so on. Okay, so these were the things about metric map, right? So now we go into topological maps, which we touched upon briefly as well last time. So this time I take an example of a metro map from the Helsinki area. So this is the suburban metro in Helsinki, this is just a simple metro route because, as you know, Finland is like Helsinki doesn't require a very convoluted metro map like one would find in Paris or London. So, and if you have observed a metro map that they have inside, is basically, or if you look at this thing here, this is not giving you much information about the distances. I mean, okay, you could make some sense of like this distance is longer between these 2 points and this is shorter, etc. But it's not giving you the exact metric as to how many kilometers is the distance between any 2 points on this line, right? It's just saying relationships, right? So if this was a location, it's just saying this location is after this if the metro is going that way, and so on and so forth. Like this location is to the left of this, etc. And distance is encoded in the edges, as I'm saying, so you could look at them and you could perceive like this is closer, this is farther, but this is just a more abstract representation of the relationship between what is where, what is to the right, what is to the left, what is closer, what is farther, as opposed to the exact metric representation. And that's why it is called topological. So it's just representing the topology. And if you were to look at the map in this case, so as opposed to the previous case where you start to get things like floor plans or building representations that look more like the building itself, in this case, you're just going to end up with graphs. So sometimes it might get really challenging to figure out if the graph is actually accurate or not. So one way to do it is to overlay this on the exact actual metric map of the environment and try and see if it's making some sense or not. Yeah. So we've talked about metric maps, topological maps, but there could also be hybrid maps, which we are going to call as topometric maps. And the question for you is, what kind of information would a topometric map represent? And now that you know what a metric and topological map is, so what would you borrow from each of these maps to get a topometric map, which is going to be a hybrid representation? So think about this and comment down below. So as always, you refer to the pop quiz number and then you drop your answer there. And if you want to upload some images or attachments or representations or whatever, you want to have a more detailed discussion, which is not possible just with a textual comment here, you're also welcome to join our Discord community, the link to which is going to be in the description and also in the channel description as well. So feel free to join us there and have a discussion with the fellow learners over there. Okay, so far we have talked about state estimation and mapping. Now we're going to talk about the next thing, because remember, mapping assumed one thing, that you know where you are, right? Now this is going to be the completely opposite thing. So assuming that I give you a map, right, you have to figure out where you are on that map. And this is known as a localization problem, where what you're trying to figure out is the robot pose. Okay. And also to some extent a goal pose, because you want to understand, okay, where you are, where you need to go, and only then you're able to plan a path on a map, assuming it's given to you, right? And there are typically two kinds of localization, local and global. So let's quickly look at what's the difference. So local localization is often known as pose tracking, right? And sometimes often known as path integration and dead reckoning, which is from other domains. Let's say sailors use dead reckoning, or in psychology, maybe sometimes you're going to use the term like path integration, which it's these are synonymous to what we're doing in pose tracking. And the main idea here is that, you know, the starting pose of the robot is known. Let's say you know the coordinates where the robot starts from, you also know the orientation where the robot starts from, and then it takes off, and then you are trying to head towards a goal. And you know, at every particular time instant, you know the velocity that you have been following for that amount of time, which means if you integrate that out, you get a distance. Okay, so after v1 for time t1, you would be here. After following v2 for time t2, you would be here, and then here, and so on. Which means if you know the start location, starting pose, you are just integrating out the rest of the velocities across the path to get the current location, right? So the problem is you're trying to evaluate the probability that your state is X given a map and your observations from 0 to t. Now, the previous slide had this one assumption that there were no noise or uncertainties involved. That's why you are always able to predict quite accurately your current pose. But let's say there are environmental disturbances such as wind gusts, etc., or sensor is always noisy, right? So whatever is going to be your estimate, again, we bring in this ellipse, which basically means there would be some region around the actual ground truth location, ground truth pose, where you're likely going to be. And the size of this region is basically the amount of uncertainty you have. And the reason why it is called local localization is because your uncertainty is bounded to your current pose, and that's why it is local and confined to the region near the current true pose, right? And the alternative to this is global localization, which means the case where you have absolutely no idea where you're starting from, and then somebody tells you to go to the goal, and then you would have, again, no idea where that goal is. Is it here, or is it there? Because you know absolutely nothing about the environment, right? So, I mean, you're given a map, but you don't know where you are with respect to the map, which means you're going to struggle to go anywhere from there. So as opposed to pose tracking, because there's nothing to track, you don't know the pose, this is now called pose estimation, because the robot pose is unknown from the start. So you have to estimate it first and then update it accordingly. Now, to put things into perspective, this is the same as this pin the tail on the donkey game that we used to play when we were kids. I'm hoping some of you, or quite a lot of you, might be familiar with this game. For those of you who don't know what this game is, let me use this as an example to illustrate what local versus global localization would look like. Okay. So if you go to some fair or outdoor events, or maybe some house parties, etc., there is this game where you print out a donkey, and the tail is given to you separately, right? So with a pin, and the objective here is that you start from some starting point, let's say somewhere here, somewhere a bit far away. You're initially shown where the donkey is, then you're blindfolded, and then you're asked to go close to the donkey and then pin the tail on the donkey. And then, you know, oftentimes people miss it by some amount, and that's why they don't hit the bullseye, and then it's like a very funny game because the tail is always in the wrong position. What makes it interesting is, you know, how things are evolving and how people make it challenging. So if you've observed where the donkey is and you know where you're starting from, you're just doing local localization. Even if you are blindfolded, you have a good understanding of where you're starting from with respect to the donkey, right? It's a local reference frame. You don't know your global GPS coordinates, but still it works, right? Because within that local frame of reference, you just want to see, okay, it's somewhat that distance away from me. And if I start from here, even if I'm blindfolded, I know how much distance I cover for each footstep, and then in how many footsteps would I get there. And then you're evaluating how high should I move my hand, and then you place the pin on the donkey. That was local localization. Now, to make things challenging, of course, people don't let you do it that easy, right? So when you start off, what people do is they make you spin around in circles. And as I told you, the more you spin, things get very interesting, and you're likely to get lost quite often. I'm not going to answer why, because that's a pop quiz for you. But yeah, you're going to get lost, right? So after spinning a few times, when you start walking, you have lost track of where you're starting from, which means you're now doing global localization. So first you have to figure out where you're starting from, then you have to figure out where the donkey is, and then do the full pose estimation as you're going there. And this gets even more challenging because you do not get sensory feedback. Your eyes are blindfolded. And the people in the audience are going to give you faulty auditory cues. They're going to tell you go left, go right, but often, just to tease you, they're going to give you conflicting advice, and then you have to figure out by yourself. So this is how you can try and understand on a more intuitive level what is the concept of local versus global localization. So I hope this example made some sense and you get some context of what local versus global localization is. Now, the thing for you to understand is, everybody knows what a global positioning system is. And there is this word global in there, which means if you use a GPS, maybe you don't need to do the global localization problem, but maybe you do. This is what I'm trying to ask you here. Can we simply mount a GPS and be done with the localization issues and say, okay, I always know where I am as a robot? And to give you some breadcrumbs to get the discussion started, think about indoor versus outdoor scenarios. And that's all I'm going to tell you at this stage, because if I say anything further, you'll probably get the answer way too quickly already. So yeah, basically, if GPS solves all the problem or not, that's the thing that you're asking yourself here. Okay. Now, localization also has this concept of loop closure, which basically means, let's say you start from here, right? And let's say I tell you the path that you need to take. So you go forward, then you go here, you go here, you go here, you go here. What happens sometimes is, as I said, because the wheels might slip, you might not turn full rotation or things like that, so that they use some sort of error in where you are versus where you should be. There might be a bit of an offset between where you are and where you should be, right? So maybe you went back to your position where you started from, but because of the error, maybe you think you're not there. So you kind of slightly offset. But as I said, if there is a landmark to help you correct for this, you will end up closing the loop. So this dotted line is essentially where this arrow should have been, which means you have done a full closed loop. And basically, whatever is the error here, you can then back propagate in all the previous errors, because their errors is cumulative. And then you could correct for all the drift that you have acquired along the path. One thing to note here is that I'm just using the starting location as an example to close the loop, but it doesn't have to be a start location. Maybe you revisited one of the previous locations. Maybe you revisited here. That would also be a closed loop that goes this way. As long as you recognize that you are revisiting one of the places that you have visited before, could be any sensory feedback that tells you this. That is known as a loop closure, and the robot needs to be able to tell, oh, right, I remember this place, right? So it can suddenly relocalize itself in case if it gets lost. That's like your safe zone. So imagine you're exploring the environment, you think you know where you are, right? So you keep going somewhere, and then something happens. Maybe your sensor goes down for a while, or maybe your some camera or something is damaged, which basically means you get lost. You have no idea where you are, right? So suddenly it's a global localization problem. So what you could think about doing is trying to retrace your path and go to the last known location, and then start again from there, so that you have a sense of your bearing, where you are, what you're trying to do, so everything starts to fall back into place. So it's like a fail-safe. And another interesting thing that we do is this problem of kidnap robot, right? So as the name suggests, let's say it is typically useful in aliased environments, and we've looked into aliasing in the perceptual pipeline, right? So the same concept applies here. Consider this scenario where there are two identical rooms connected with a corridor, right? This is our kidnapper, and this is a robot in some location in room 1. Now, let's say the robot was given a certain task. I don't know, maybe to vacuum the robot room or something. So it was doing something there. But in the middle of whatever it was doing, you suddenly teleport the robot to another room. And since it is identical, the robot doesn't know that it has been kidnapped and teleported into another room. So it would start to, continue the task from wherever it left off in this room, but instead in the room 2. But at some point, the robot is going to realize, imagine that it had vacuumed, let's say, half of the room here, but this entire room was dirty. So when it went back to the first half, it realizes, wait, I vacuumed this area. How come it is dirty, right? So this conflicting signal needs to tell the robot, like, oh, something changed, something happened. What happened? Maybe this is not where I'm supposed to be, which means the robot is doing two things. One, it is detecting that it is lost because the things have changed, but it did not see that from the sensor because, of course, it was blindfolded, kidnapped, and teleported to another room, which looks identical. So you were a bit evil, and you did this to kind of, push the robot into getting lost, and then it needs to recover from it, which is the step 2. So once the robot has recognized that it is lost, it needs to recover from it, and then once it knows where it is, it was vacuum cleaning and it continues to vacuum because it knows where it is and it knows where it is going. But then once it is lost, it means now it has to do global localization because it is lost. It doesn't know where it is. It doesn't know anything. So it needs to start from scratch again and relocalize before it can continue the mission. Right. So this is known as the kidnap robot problem. And typically, in a real world, the robot never gets kidnapped and teleported like this. I mean, okay, sure, the robots lose signal, they do some haphazard actions and something, but they're never teleported into another location like this, right? So this is a very important test of something. And this is what the question is asking you here. In real life, this is next to impossible that the robot would get kidnapped like this, but this is a very useful aspect to study. Why is that the case? What do you think becomes apparent if you are trying to use the kidnap robots problem on your robot and test it out? What kind of hypotheses are you testing, and what would the test results reveal in such a case? So think about this and answer in the comment section below. And unfortunately, the terms active and passive, as we have seen before, get used in a lot of different contexts in robotics. And aside from sensing, and also in sensing, we saw like what active passive means for a camera versus what it means for whisker-like tactile sensors. Here also in localization, active and passive means slightly different things. So active no longer means it's emitting any sort of energy, but active means that it's to be honest, personally, I like to call it reactive, but what it means is like once the robot is taking an action in a current state, the action are taken not only to go to the next state arbitrarily because it's a free state, etc., but to minimize the localization error as quickly as possible. So your actions affect how you are able to localize and how quickly you're able to do it. Now, if these two things were decoupled, that basically is passive, which means it's just an observer. So you took an action, you perceive the environment. From after that action, you go to a new state, you perceive the environment, and then you try to relocalize yourself, and this is done standalone. But if your action is taken keeping in mind that you not only want to go somewhere but also want to localize yourself quickly, so there's an objective attached to it, that becomes active localization. So just keep this in mind, that there is also the concept of active versus passive localization. Now, we talked about uncertainty in the past. We also saw there is uncertainty when you're trying to do the state estimation, right? So the thing is, oftentimes this uncertainty is a combination of a lot of different things. And the way I like to think of uncertainty is like, you would get this joke if you are a Game of Thrones fan, right? So the reference here is that I don't always know things, but when I do, I know nothing or very little, right? So, but these are the various forms of uncertainty that exist that kind of makes the state estimation a challenging problem to solve. So there is some hardware uncertainty, right? So there's systematic noise, there's random noise, there's some range limitation from the sensor, how far and how much it can observe at any given time. Then there is some unmeasurable quantities that the sensor just cannot measure for you. So those are the things. Plus then there is also algorithmic uncertainties. So if you're trying to make a model of the environment and sensor models, and there are a whole bunch of models involved when you're doing state estimation, so there are model uncertainties, right? So because model is something that you think best fits the data, but maybe that's not the best model to have, and you have certain assumptions on how the noise propagates in that model, but maybe that's not ideal because nobody's telling you the ground truth of how things look like in terms of models and noise and uncertainties, right? So there are various sources of uncertainties, which is what makes it challenging to be able to do state estimation. And the solution to that is to look into what is called as filters. Now, the filters are broadly classified into three different categories. There is spatial filtering, which means at any particular time instance, there are multiple sensors. Not necessarily the same sensor, could be a collection of sensors, like a heterogeneous collection of sensor, or could be homogeneous. So in terms of whiskers, I like to give this example, like there could be multiple whiskers, like a whisker array, and at every time step, multiple whiskers give you some sensor reading. Or it could be done this way, where you have one whisker, but it gives you different readings at different time steps. I mean, different sensor measurements, right? So it doesn't necessarily have to be distinct sensor measurements, but from different time instances. But there could also be spatio-temporal filtering where you combine both of them. So there's a whisker array that gives you a whole bunch of information at every different time step, right? So these are typically what the filters are trying to do. So they're trying to combine information from multiple different sources, could be homogeneous, could be heterogeneous, across space and time, to try and minimize the impact the uncertainty has on you being able to estimate the state, where what is inside the state is context dependent, right? And filters, let's say we could broadly think of this as this hierarchy. So you could have combinatorial filters, which deal in terms of, like, let's say, set theories. And then they could have Bayes filters, which deal in terms of probabilities. And then you could further subclassify them as maximum likelihood filters, Gaussian filters, particle filters, and hybrid filters, which is a mix of particle filters and Gaussian filters. And Gaussian filters can further be classified as Kalman filters, which are very, very prominent in terms of state estimation. We're gonna discuss them in the coming lectures. Gaussian mixture filters are also there, and Kalman filters has had a few extensions over the years. And this is like, because it's a very prominent concept and it's like a go-to problem to do the state estimation and combine data from multiple different sensors. And this is recursive in nature and probabilistic in nature. So it's a very well-adopted concept as well. So we're gonna look into these things in the coming lectures. And one thing that I do want to clarify at this time before we wrap up today's lecture is the misconception of the word filter, right? So when you think of the word filter, oftentimes people think of this concept of a coffee filter, where you're trying to throw away things that are not relevant to minimize the noise, right? So you don't want coffee grains inside your coffee, so you throw them away. Instead, what you should think about filter as a sort of this, infusion of different sources, where the fruits are inside this tube, the infusion tube, and the water picks up the combined taste of all of these fruits without the seeds and the solid part of the fruits mixing into the water, right? So you could drink it without having to strain it. So instead of thinking of filters as throwing away things, you could think of them as fusing things. And that is what essentially we are trying to do. So when we are trying to use a Kalman filter or whatever filter from the previous hierarchy we are seeing, we are trying to do this, where each of the fruit slice represents a certain type of sensor. Could be more than one sensor of the same type, as I said, or could be heterogeneous combination of sensors. But you're trying to combine all of this by minimizing the impact of noise any one particular sensor would have on this fusion. Right. So let's say there is a typical kind of fruit that you don't like so much. Maybe the taste is too sour, etc. But if you have a combination of different fruits, and that fruit that you don't like has a lot of good vitamins and minerals in there, you can still have that, with the water. But the other fruits are going to dilute the effect that one particular fruit has on the entire flavor. So that's the concept here. And then, how much of each of the other fruits that you want, and There are different kind of aspects of, what would be the resultant taste of this water, which would be the dominant flavor, etc. So those are the kind of things we're going to look into the upcoming lectures, right? How do you fuse the information from different sensors? Is there one particular sensor that you weigh more than the others, or is every sensor treated equally, etc.? So be very careful with the term filter, which is often used in terms to represent fusion. But since Kalman filter has the word filter in it, and most particle filter has the word filter in it, so most of these words, filters, came up first, and then we started using them for fusion as well. So they serve dual purpose, right? So throwing away things that are not relevant, reducing the noise, and combining information across sensors. That's why. So there is this caveat. So just be careful with this, right? Okay. So with this, we're going to wrap up today's lecture, and that's not the end of the discussion here. So as I said, state estimation, recursive state estimation, there are a lot of these filters which we haven't gone into much detail and understood things yet, but it was just like a high level overview of discussion to be continued further, right? So in the coming lectures, we're going to go into a bit more detail of what these filters are. And we're going to talk about this very hot topic called SLAM, which is simultaneous localization mapping, right? So in today's lecture, we saw mapping first, then we started seeing localization. So localization, you could think of yourself as, as a tourist in a city where you go to the information center and they give you a tourist map with some landmarks mapped on it. And then you try and look at the map and you try and figure out, okay, with respect to this map, where are you at this time? Oftentimes it's very prominently labeled there and says you are here, which is your localization, right? So yeah, we looked at these two things separately, but essentially not every time you have a map given to you, right? So when you're in a completely unknown environment, there's no map, you don't know where you are, and you have to do both these things at the same time. So we're going to look at these kind of problems in the coming lectures and try and figure out what does this thing entail. So thanks so much for listening for today's lecture, and be sure to like and share this lecture with fellow learners, as it helps with the algorithm to promote this lecture to other learners as well. And be sure to subscribe to my channel and hit the bell notification so that you're notified as soon as the next lecture goes live. That's it from my side. Thank you and have a nice day, and I'll see you next time.